Today we're going to talk about magnetism. A magnet is any material that attracts certain other materials. And the magnetic pole is one of the two ends of any magnet. All magnets, and I do mean all magnets, have two poles, a north pole and a south pole. Magnets can come in various shapes, sizes, and strengths. Despite their shape, size, or strength, they will always have two poles, a north pole and a south pole. There is no such thing as an isolated pole or a monopole. The law of magnets is much like the law of charges. Poles that are opposite, that is north versus south or south versus north, attract, whereas poles that are like, two norths or two souths, repel. North and south poles always occur in pairs. If you cut a magnet in half, then you will have two magnets with two sets of poles. If you cut that in half, you will have two magnets with two sets of poles. And even down to the molecular level of a single atom, it will always have two poles, a north pole and a south pole. These can never be separated. Material that demonstrates strong magnetic effects is called ferromagnetic. Now, heat or trauma can cause the material to lose some of its effects. The Curie temperature is the temperature that you heat a magnet to that causes it to lose all of its magnetic properties. A domain in a magnet is a microscopic area in ferromagnetic materials that has poles. And here's an example of several domains. Section A here is a piece of iron, which is a ferromagnetic material, that has no magnetic properties. And that is because the various domains, as you can see here, are all oriented in different directions, and thus the overall effect is that there is no magnetic effect. When a material is magnetized by an external magnetic field, then the domains begin to align. And some grow in size at the expense of others, so they incorporate new domains within themselves. The individual atoms within these domains align, and each atom acts like a tiny bar magnet. Now, electricity produces magnetism. An electromagnet or electromagnetism is the use of electricity to produce magnets or magnetic fields. This picture here is a MRI machine or magnetic resonance imaging machine. The outer part is a huge, very powerful magnet. What happens is they pass electricity through a coil in such a way as to produce this magnet. And when you put a person inside this magnetic field, you can cause their tissues, the atoms in their tissues, to line up in various directions, and the magnetic fields produced by that can be read and produce images. A device that is used to make a magnet is turned into a magnet using electricity is called an electromagnet. Now, what you see here on the left are iron filings near a continuous loop of wire that has electricity passing through it. On the right is a bar magnet. And what is demonstrated here is this current carrying coil and the bar magnet have a field shape that is very similar and can cause the iron filings to form a certain field representation. These responses are very similar, and therefore you have, by the passing of current through a coil, the effect is very similar to the presence of a bar or magnet. You can also wrap a coil around ferromagnetic material and turn that ferromagnetic material into a bar or magnet. An electromagnet with a ferromagnetic core can produce significant magnetic effects depending on the current that's passed through. This happens because the electrical current causes the alignments of the domains within the core, and the poles are aligned with the electromagnet. The current must be, and this can't be the current must be in motion to generate electromagnetic field. Motion has to be present for an electromagnetic field to occur. If you use the planetary model of an atom, the electrons orbit the nucleus and form a closed loop current. That is what produces the magnetic field with a north pole and a south pole. In other words, you have this electron in A. It's moving clockwise around the nucleus. The motion of that electron produces the electromagnetic field within the atom, and the reddish lines represent the field that's produced. Electrons also have a spin, and this can be shown as a rotating charge, and this is shown in B. And this also is what produces the electromagnetic field with the north and the south pole. Now, the planetary model, or the spinning electron, is not entirely accurate, but it does provide a way of understanding the phenomenon that we observe. Magnetic field lines are defined to have the direction that a small compass points when located in a field. And what the direction is that it always goes from the North Pole to the South Pole, a North Pole to the South Pole. If a small compass are used to map the field around a bar magnet, they will point in the direction shown in A, away from the North Pole and toward the South Pole. B is just substituting for all these little magnets a line that shows the continuous magnetic field, and this is called a field line. It's very much like an electric field line. The strength is proportional to the closeness of the lines, or the density of the lines per unit of area. If the interior of the magnet could be probed, the lines would be found to form a continuous closed loop, and inside the magnet they would be essentially parallel. Small magnets could also be used to map the fields in this setting. And what we have in A is a magnetic field that goes in a circle, electrical flow that goes in a circle. You have the fields mapped out in the two circles around that. So a magnetic field in a circular current loop is similar to that of a bar magnet. If you have a straight current, like shown in B, then the magnetic field forms a circular loop around the straight current. And this can be represented by the right-hand rule shown in C. If the line or the current is in the plane of the paper, the field is perpendicular to the paper. you use your right hand pointing your thumb in the direction of the current, and your fingers curl around representing how the field would go. It comes out of the page on the left of the wire and goes into the page on the right of the wire. When it's coming out of the page, you see the tip of the arrow, or a dot. When it goes into the page, you see a crosshatch, which is supposed to represent the tail of the arrow. Now this is a diagram showing another way of representing the right-hand rule. And here we have a charge traveling west through a field which is directed to the north. And in this, we use the right-hand rule to determine the direction of force. The direction of force is determined by using the right-hand rule, where you point your finger, index or middle finger, usually I use my middle finger, in the direction of the field, and the thumb in the direction of the charge. And then whichever way your index finger naturally points, in this case down, is the direction of the force. The force of a magnetic field can be described mathematically on a moving charge with the following formula called the Lorentz force. And that force is equal to the charge times the velocity of the charge times the magnetic field that it's passing through times the angle, sine of the angle between the direction of the charge and the direction of the field. Now in the diagram here, what we're looking at is the charge is moving due west and the field is due north, therefore the angle is 90 degrees. The sine of 90 degrees is 1, and so the force here would just be QVB. A positively charged object moving due west in the direction of the Earth's magnetic field, which is due north, experiences a force that is straight down. A negative charge moving in the same direction would be straight up. Okay, so if it's a positive charge, it is in the direction that your finger would point. And if it's a negative charge, it's opposite the direction that your finger would point, using the right-hand rule. Here's another example. Magnetic fields exerted on moving charges. This force, by the way, Lorentz force, is one of the most basic forces in nature and in physics. The direction of the magnetic force on a moving charge is perpendicular to the plane formed by the velocity or movement of the charge and the magnetic field, and follows the right-hand rule as shown. In the case with his palm up, as shown here, the force would be straight up if it's a positive charge and straight down if it's a negative charge. The magnitude of the force would be QVB times the sine of theta, but since it's perpendicular and theta is 90 degrees, the sine being 1, then you do not have to take that into account. Now, before we move on, let's do one problem in this regard. Suppose a positive charge of 2 times 10 to the 10th coulombs is moving 10 meters per second due west in the Earth's magnetic field. What is the force exerted on that charge, and what is the direction? So if we do this, first of all, we have Q is equal to 2 times 10 to the minus 10, positive. V is 10 meters per second, 10.0 meters per second. B is 5 times 10 to the minus 5 Teslas. And so F is equal to QVB, And since it's west and the Earth's field is north, sine theta is 1, so we do not have to include that. So this is 2.00 times 10 to the 10 times v, which is 10 meters per second, times b, which is 5.00 times 10 to the minus 5. And all that multiplied together is going to give you 1.00 times 10 to the minus 13. And as shown in the diagram here, if you put your finger in the direction of the field and your thumb in the direction of the velocity, this finger would point straight down. And so the direction is down.